I can do one thing in the lab once. When there are 8 billion people involved, I have to be able to do it in the lab 150 times. And then I have to be able to do it 150 times cheaply with chemicals that are sustainable.
What is your name? Where do you work? And what do you do?
My name is Marc Secanell. I work at the U of A in the Department of Mechanical Engineering. And I work in electrochemical system simulation, design, fabrication. The name of the lab that we use now is Electrochemical Energy Systems. And we basically try to combine experiment and simulation to design better energy storage devices that use electrochemistry. So fuel cells, electrolyzers, some working batteries as well. Accelerator is based on alkaline electrolysis. The idea of moving to alkaline for us was that in acidic media, there are very few catalysts that can do water splitting efficiently, and you're left with iridium. So usually what you would do is you would mine platinum, and one of the byproducts of platinum mining is iridium. Catalyst companies have written reports discussing the fact that with the current targets that we have from the International Energy Agency, you might not have enough iridium. Moving to alkaline, you have a lot more materials. So nickel iron, cobalt oxides, there's a lot of different materials that are actually quite active under alkaline conditions, so at very high pHs. Reading the literature, I noticed that while proton exchange membranes have been there since the 60s, there weren't any alkalines. Recently, there were a couple of companies that had to spin out that were able to create membranes that would transport the OH groups. So we wanted to take advantage of that, and that's how we started with the alkaline. So in that, what's new, the membrane is new. So we work with a company that just is 4 years old. The catalysts that we use are slightly different. And again, trying to understand the architecture again. Very few people have done it. So I think the first paper I saw was 1960s. Bockris, in a letter in Science, he already said one day we'll have offshore wind turbines that will be coupled with an electrolyzer, and we will split water to make hydrogen that will pipe in. And now there's some hydrogen hubs in the US that are trying to do the same thing, projects in Europe trying to do the same thing. So it's not new, it's now 60 years old. The critical issue is on the details of the technology. The question is, can you make it reasonably priced with abundant materials and so that the system lasts a long time? And that's where I think research is required. So a hydrogen electrolyzer is a device that contains 2 electrodes, a positive and a negative terminal. On the positive, which is usually called the cathode, is where you have, in a proton exchange membrane system, protons combine to form hydrogen gas. And on the anode, you basically feed in with water, and then the water absorbs on a catalyst, breaks into protons and oxygen molecules, and the oxygen molecules leave. So it's much like a battery. The difference, I would say, between an electrolyzer, a fuel cell, a flow battery, and a real battery is that we still have the 2 terminals, we still have a separator, but we have to flow the fuel and the reactants in. It's not all self-contained into a box. Instead, we have to have 2 reservoirs, and we flow. Something comes in, something comes out. The materials that are suitable for a fuel cell are not suitable for an electrolyzer. Try to run a fuel cell like an electrolyzer, you're gonna get no hydrogen, and you're gonna break the fuel cell. So they are very different devices, yes. So that's the voltage that you get from the solar panels, but this is actually getting applied to the cell directly. So if you notice, I connected the 2 panels in series, and then the positive and the negative terminal are going to the electrolyzer here. So if you look at the side, can you see there the little bubbles that are being formed? What you're trying to do is simulating what would happen during the day if you connect an electrolyzer to a solar panel, right? You could do what we're doing now, which is basically all the power from the solar panels going to the electrolyzer, and then you're forming a lot of hydrogen. In this case, you can see the hydrogen is getting accumulated in this reservoir and in this reservoir. I have the little house, which is my load. You could still say, well, half my load can go into the electrolyzer, and then half my current can go to my load, which in this case would be the house, right? So now you could power your little house while still producing small amounts of hydrogen. Renewable system doing is you would oversize the solar panels or the wind farm, and then when you have excess energy, you provide the excess to the electrolyzer. So this can actually work in mixed loads. And then while this is happening, you will form your gases. Eventually you will have enough hydrogen on the reservoir. But now basically what we're doing is generating hydrogen. It will get into these little reservoirs, and then we will be able to connect these to here and power the fuel cell. Even though they look the same, the catalysts are completely different. So if you run a fuel cell, you run from 1 volt down. When you run an electrolyzer, you run from 1 volt, about 1.23 volts up. If you run down, you can use certain materials like carbon, which is cheap and doesn't degrade. When you run up, carbon corrodes to CO2. So that means that one side of the cell has to be completely redesigned. There is big difference between materials. So the main materials that you need to consider when you're looking at an electrolyzer is the membrane, which would be, again, PEM meaning proton exchange membrane or alkaline exchange membrane. And so PEM, the material is Nafion and is very well studied. Alkaline exchange membranes are actually quite recent. Only in the last decade they've been stable enough to be able to make an electrolyzer. So that's one thing, and there is a big difference. PEM is very stable, very durable. AEMs are better for the environment, but they tend to be not as stable yet, and they require some fine-tuning of the reactants. The second difference is the catalyst. So again, the catalyst are different from the anode and the cathode, and could be precious metals or non-precious metals. Precious metals tend to work better in PEM. Non-precious metals work quite well in alkaline. Non-precious are cheap. They don't seem to work as well as the precious metals. That's where we try to do research to try to make something that is cheap and doesn't work so well work well. What we do in the lab is not actually the device, which sometimes we do, but we spend all of our lives in the layer in the middle, because that's where all the voltage losses take place. And so that's the one that if you can optimize it, a lot of electrolyzers will have 100 cells. So if you optimize the performance of one of these, then that gets magnified by 100 times.
How is your method of inkjet printing different than other methods for producing electrolyzers?
I think the main difference is it gives a lot more control and a lot less ink wastage. So this is the ink that will go into the inkjet printer. And this is basically a mixture of different chemicals. Usually the solvent is isopropanol, water, sometimes methanol, some alcohol that can evaporate, and a thickener that we use to make sure the viscosity is right for the printer. We have these inks properly done. Once we have it, we basically take a syringe, fill it with the inks that you see there, and then just put it into the cartridge. Fill this reservoir, which contains about 1.5 milliliters of ink. This is where we leave most of the inks to settle. This is if you want to leave the inks a long time and you also want to just do some mechanical mixing. You can also rotate in this way, right? So sometimes you put little balls, zirconia particles, and then between the particles they grab and crash and break the catalyst. This side here is just to answer a simple question: will this ink jet or will it not jet? So this is called a dynamic light scattering machine. So what it does is you can put the ink in one of these little cuvettes, and then you can shine light, and by looking at the light that gets reflected, depending on the shift on the wavelength, we can figure out how big the particle size is. You can actually get a probability of particle size. And so what we do here with our inks usually is we do this experiment multiple times, and then we can make sure that either the experiment is repeatable or if there is any settling. So if the particle size is changing towards bigger and bigger and bigger and bigger, then we know that the ink is not stable and that when we put it in there, it will not eventually jet. Again, because you're trying to form little droplets, you have the right surface tension and the right viscosity. We have this method that the only thing that we do is we put inks and we look at how long it takes for the drops to fall. And then for viscosity, we can put an ink here and then we measure how long does it take to fall through this cavity, and then we can again get a rough estimate of viscosity. Any lab in the world comes and says, I want an electrolyzer of any shape, we can make it. So we even printed the logo of our lab with the printer, right? And we can make an electrode like that. We can make electrodes that follow a channel. So we have a lot of flexibility on how we print, how much we print, we can create the structure. We do now a functional electrode where we put different catalysts in different parts of the electrode. That's the advantage. And then the catalyst wastage is another big one. Like my batches of ink, you can see it there. It's like 1 milliliter is enough, which is milligrams of catalyst. Most people will use grams, and so you spend a lot of money that is unnecessary. The disadvantage is it's slow, and to make the inks takes a long time. I think the benefits for a research environment outweigh by far the disadvantages. The other advantage actually that people don't talk about much is also safety. We don't have a lot of people spray, and then you have all these nanoparticles that are floating. We only have one drop at a time. So it's also safer for all the students that work in the lab. Well, the two biggest challenges, I think, is making people understand that the devil is on the detail. And then the second one is to fit in an environment where there's always a competition between commercial enterprise and morality. So if you're working in energy, there's always this, I want to save the environment, but I want to make money. I want electric vehicles, but I will put 100% tariff on electric vehicles from other countries because I need to protect my economy. I want hydrogen, but it has to be from natural gas because I need to sell natural gas. So this duality, I think, is painful because then it's very hard to frame your research and even think about the big picture. And then the other one is to make people understand that hydrogen is not new, but that doesn't mean that there is no research to be done. The devil is in durability, in the right material, how you deposit that material, and that requires the skill that sometimes is hard to have, depending on who you talk to. Yeah. So I wish people would remember that we're 8 billion people in this planet, and that means that it's not going to be an easy transition. I wish too they would remember this duality between commercial success and morals and success of the species, I would say. Just because one thing works in the lab doesn't mean that it will work at an 8 billion people scale. We actually work with the National Research Council of Canada. We work with Ionomer, which is a startup out of Simon Fraser University, and Simon Fraser University as well. We work with another national research lab in Germany, which is the Fraunhofer IFAM in Dresden. We work with Sunfire, which is a German company. Ahmed Qureshi is an additive manufacturing expert, and then he's also helping us to make part of the cell. So we basically have formed a team where we have expertise in all areas. That's what you need these days. You need large teams to be able to cover all the different components and make sure that you have some uniqueness.